Okay, here we're going to talk about vertical asymptotes and also infinite limits. So here's the brand new stuff here. This we've seen before, right? When we see this statement, the limit of a function as x approaches a is equal to L, what we assume here is that L is a finite number. So it's really telling us if x approaches a, then y is going to approach L, and L is assumed to be something concrete. So the difference here in this lesson is L may not be something finite, right? L may be infinity, right? Might be positive infinity or negative infinity, but this is not finite. And when this kind of thing occurs, we say that this limit fails to exist, right? So in this case, we could say the limit does not exist. And that's really what this lesson here is all about. Okay, so we're going to take a look at an example. Right, and this example will have some of this behavior. So it's really a good one to take a look at. So if you look at a mathematical function like this, you can tell that it's pretty well defined everywhere, but there is going to be a problem when x is equal to 2. So a big part of looking at this problem is examining what is really going on, right, when x is equal to 2. And we can try to answer this question, right? What is the limit of the function as x approaches 2? So notice you can't insert 2 into the function as you get division by 0. So you have 1 divided by 0, and that's not something that you can really compute. So the natural thing we do here, we just go back to our old tools and looking at something like a table just to see what's happening. So we'll look at a couple of tables here, right? So we want to see what's happening near x equals 2. So if you look at this table, as we've seen before, we're looking on the right-hand side of 2 and also on the left-hand side of 2, and you can see some very, very different behavior here. So it seems as we're approaching 2, right, from the left-hand side, these numbers are smaller than 2, it appears that the numbers are growing larger and larger, right? So we move from 33 to 50 to 100. And on the other side of 2, the larger side of 2, the numbers appear to be dropping, right? They're still growing in size and magnitude, but in the negative sense. Negative 33, negative 50, negative 100. So this kind of behavior, you'll notice that you don't see a clustering of values, right? The numbers here are not getting closer and closer to anything. They seem to be growing without bound. And then something you can do to convince yourself even more is you can look at a refined window, right? So this is almost the same table as we see here, except with greater precision. So now you can see that as we get really close to 2, 1.999, 2.001, we have either a very large number or a very large negative number. So this is telling us we're approaching positive infinity on this side and then negative infinity here. So I'm going to switch this out and then we can write down those statements. So what we could say here, we could say the limit of this function h of x as x approaches 2 from the left, right? So we're looking over here. This appears to be positive infinity. So we can write that statement, and then we can write a similar statement on the other side. Okay, so as we try to approach 2 from the right-hand side, these numbers are dropping, right? And this appears to be negative infinity. So this is a perfect example of where we would say that you can't calculate the limit of this function h as x approaches 2, because on one side the numbers are too large in the negative sense and too large in the positive sense. So this limit here in red does not exist. So this limit we could say fails to exist, DNE for does not exist. So keep in mind here that these limits don't exist either, right? So even when you look at the one-sided limits, this is positive infinity, that limit fails to exist. This is negative infinity, that one also fails to exist. So something you might remember from algebra, in addition to looking at the table, it's nice to look at the graph of the function, right? Because then you can support these statements or add a picture, right, to what these statements are saying. So this is saying as we approach 2 from the left, the values go straight up. And you can see that kind of behavior here. So as we approach 2 from the left-hand side, these values are increasing. Right? The graph is in blue. And as we approach 2 from the right-hand side, the values drop. So we're approaching x equals 2 here from the right, and then the values drop there. And the big idea is that this speaks to the algebraic idea of a vertical asymptote. So this original vertical line that we jotted down, x equals 2, corresponds to the vertical asymptote to h of x. And you can see that right there in the graph. So now is a pretty good time just to put the general definition up there, because this one looks very complex and involved, but it's not a very difficult definition, and we just saw it in an example. So if you look at this, it's saying if we try to calculate a limit as x approaches a, if we get something either too large or too small, so positive or negative infinity, and it doesn't matter if it's a right-hand or left-hand limit, then that means the place that we're trying to approach, in this case x equals a, this is a vertical asymptote to the original graph. And then just to call that back up, right, because we saw this in the previous example, you can tell here the limit from the left-hand side was positive infinity, the limit from the right-hand side was negative infinity. And when you exhibit that kind of behavior, you're talking about a vertical asymptote. There are examples, of course, where you might be approaching positive infinity from both sides, a similar statement for negative infinity. Alright, so the last thing I want to do here is just the nitty-gritty on an actual example. And so we'll do whatever we can with this example just to highlight the ins and outs here. So this problem is saying, let's identify the vertical asymptotes to this graph. And so I might actually end up doing a little bit more than that, but we'll just see if we can answer the question here. Okay? So you can probably tell that division by 0 are places where you could possibly have a vertical asymptote, but sometimes you get some interesting behavior. So we'll take a look. I'll just call this y, and I'll do a little bit of the algebra here. This is some pretty simple factoring. You have these two monomials here, or the binomials here, and then you have this here. And so the x plus 1, right, as long as x is not equal to negative 1, it's valid to cancel this out, right? And this will look like x minus 2 divided by x minus 1. And this is a valid statement so long as we stay away from x equals negative 1. Okay? So the things that we should be highlighting or looking for is when you have division by 0 in this problem, when we look here, it appears that x equals 1 and x equals negative 1 are the problematic points to this function, and we want to see if one or both of those are vertical asymptotes. So we could just write a couple of notes here, x equals minus 1 and x equals positive 1, and we're going to do a little bit of identification. Okay. So I'm going to show you a couple of tables here so that we can add some support to what's going on there. So when we look at this table here, this is our first attempt to look very, very close to positive 1. So when you look at this table from the left-hand side or from the right-hand side, you can see this behavior is very similar to what we saw in the previous example. These values are growing without bound, and these are dropping without bound. So it appears here, if you try to find the limit when x is equal to 1, you're going to end up empty-handed. So I'm going to write this down here. We'll just say as x tends to 1, it appears that the limit is not going to exist. Right? The limit doesn't exist. And this here is definitely indicative of that vertical asymptote, right? That kind of behavior. So if we look now at negative 1, right, the other piece. So if we look around x equals negative 1, I should make a little adjustment here. Okay. So if we look very, very close to negative 1, notice now you see that clustering behavior. So whether we're close to negative 1 on the left side or on the right side, all of these numbers in the y column are now really, really close to 1.5. So this would suggest here that as we approach -1, the limit does exist, right? It would be 1.5. Okay, so we have these two statements here. So in going back and looking at this question, it does appear that we have a vertical asymptote here because of the unbounded behavior, but this limit definitely exists by looking at a table. And what you may remember, this is good practice to look back, right, is that when x approaches -1, this is the kind of math that we would normally do, right? We would get rid of this discontinuity here, but then we would plug in -1 into the updated function, right? And this is the updated function here. And notice if you let x equal -1 now in the updated function, this would calculate to -3 over -2, right? Or 3 over 2, which is the same as 1.5. So here we have a limit existing, right? But you can't plug the number in, x equals -1, and in the other case we have a limit that fails to exist. So something I want to do here is just to put the graph up here, so that way you can connect what happened in the table and what's happening analytically, right, and with the algebra that we're doing. So as x approaches 1, we found that the limit failed to exist. So if you look at this graph, as we approach x equals 1 from the right or from the left, notice that the values are both dropping and increasing without bound. And we saw that, right, in the table earlier. But as x approaches -1, it doesn't matter if it's happening from the right or from the left, there is some regularity in the y values. So we can see that here in this graph, that there is a gap in the graph, right? So the limit is around 1.5, right, as we approach -1 from the left or from the right. So in the end, for this problem, we would say, yes, there is a vertical asymptote, right, at x equals 1, but at x equals -1, we have just a discontinuity, right, a hole in the graph. So we can say that here, this will give us a vertical asymptote. And here we just have a hole in the graph.